Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list published on February 20th, 2026, just 4 days ago. It presents a systematic breakdown of the design space for vision language action models, distilling 12 key findings into a new architecture that hits over 97% success on standard benchmarks. The paper is titled VLANeXt, Recipes for Building Strong VLA Models. And as we'll see in the figures later, the results demonstrate that principal design choices can matter much more than raw model scale. And for those interested in the implementation, the authors have shared their code on GitHub. On Hugging Face, you can download the VLANeXt checkpoints for evaluation. They offer a codebase and recipes to help you reproduce their findings and build your own strong robotic models. Speaking of those results, Figure 1 compares performance on Libero Plus on the left and standard Libero on the right. The vertical axis tracks success rate, while bubble size indicates parameter count. You can see the green bubble, representing versus VLANeXt, sitting at the top of both plots, hitting about 80% on the tougher Libero Plus benchmark. Crucially, notice how much smaller that green bubble is compared to the huge orange circle for open versus LAOFT, proving that principal design matters more than just scale. Well, Figure 2 reverse engineers that success by plotting the ablation trajectory from a basic setup to the final model. The chart divides the process into 3 phases: foundation components, perception essentials, and action modeling. Initially, the baseline starts at just 11%, but adding action chunking and a stronger versus LM backbone quickly pushes performance to 90%. At the dotted line, they switch to the harder Libero Plus benchmark to test generalization. Here, adding multi-view inputs helps the model recover, culminating in the final versus VLANeXt model at the bottom, which clearly outperforms the larger open versus LA baseline shown in orange. So while Figure 2 showed the overall trend, Table 1 details the specific gains for each component. In the policy module design section near the top, switching to a large policy module triples the baseline performance to 64%. Further down, under Action Learning Objective, continuous methods like regression outperform discrete classification, pushing scores to 85%. Then, looking at perception essentials, adding a wrist camera for multi-view significantly boosts robustness. Finally, the last rows show that applying a frequency domain loss, which helps the model capture the smooth rhythm of movements, yields the top score of nearly 93%. Figure 7 brings all these components together into the full versus VLANeXt architecture. At the bottom, the model processes 3 inputs: the robot's historical proprioception, or internal state, along with the text instruction and multi-view images. These inputs are tokenized and fed into the multimodal large language model, which uses soft metaqueries, shown here as orange squares, to bridge the gap between high-level reasoning and control. On the right, a diffusion head uses these queries to generate precise action chunks from noise. Finally, the frequency plot at the top illustrates the auxiliary loss we just discussed, which regularizes the output to ensure smooth, stable movement. Alright, moving from the architecture to the results. Table 2 compares versus VLANeXt against standard baselines on the Libero benchmark. The top section lists direct policy models, like diffusion policy, which hover around 75% average success. In the middle block, we see various VLA competitors, where the previous state-of-the-art, open VLAOFT, reaches 97.1%. However, looking at the bottom row, VLANeXt edges ahead with the highest average of 97.4%, securing wins in both the spatial and object categories. Well, while the previous table covered standard tasks, Table 3 puts the models to a much harder test on the Libero Plus benchmark. This suite measures robustness against unseen perturbations listed in the columns, such as changes in lighting, camera angles, and background clutter. In the top section, we see that standard baselines like OpenVLA struggle heavily, averaging only 15.6%. Moving down, the previous state-of-the-art OpenVLAOFT improves this to nearly 70%. However, VLANeXt at the bottom takes the lead with an 80.1% total success rate, showing massive gains in the camera and robot categories specifically. Wrapping up, the big takeaway here is that we can stop assuming bigger is always better for robotics. By refining how models perceive and act, using things like flow matching and multi-view inputs, versus VLANeXt outperforms giants with a fraction of the parameters. This recipe offers a reproducible path forward for the whole field. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.